Okay, good morning, everyone. So today we're going to cover two chapters. So we have the monoprotic and polyprotic acid. Okay, so you have already done this uh, topic during your Gen Chem 2. So maybe to some of you, this is just some sort of a review. Okay, but we're going to dig into some things that I can say is new to you. Okay, so let's try to have a review about acids and bases and some concepts related to acids and bases. So for instance, okay, if you recall, there are lots of definitions of acids and bases, right? So you have here Arrhenius definition. So Arrhenius definition, acids are anything that forms H plus or H3O plus when dissociate in water, while bases are the one that form hydroxide ion when dissociates in water, which limits the bases to just the hydroxide. And then you have the Bronsted-Lowry definition, wherein acids are proton donor and base are proton acceptor. Okay, and then we also have the definition by Lewis of the Lewis structure PAME. We define acids are electron pair acceptor, while base as electron pair donor. So that's one of the stuff that you need to know about acids and bases. And you also have the concept of strong acids versus weak acid or weak base. So what's the difference of the weak acid and strong acid? Anyone? When we're talking about strength of the acid, you can type your answer in the chat or you can let your voice be heard. What's the difference between strong and weak acid or bases? Okay.
Yeah. What Hambo said. He said the strong acids and strong bases, they completely disassociate in water.
Okay. So when you say strength of the acids and bases, it has something to do with dissociation. It has something to do with their ability to ionize. So when we say strong acid, strong base, there's 100% dissociation. So even though they're covalent compound, they act as, or they act like ionic compound. Weak acid and weak base, on the other hand, they have what we call less than 100%, some is even around less than 1%. Okay, so that's the main difference between a strong acid and weak acid. And what else you have learned from the acid? You learn this concept, okay? pH is equals to negative log of H plus or H3O plus, and POH is equals to negative log of OH minus. Okay? Now, how do we identify strong acid from weak acid? Anyone? How are you going to identify strong acid and weak acid? Still remember? Okay, so there's a small list of strong acid. In fact, in Gen Chem, you were asked to memorize 6 or 7 strong acids. And if they're not included in that list, you can say it is a weak acid. Okay? Now, what else? How are you going to know if You have a given weak acid or a given weak base. What other information that is usually supplied to you?
Maybe reaction with water is like irreversible.
That is for strong acid. But what
Yeah,
else? Once that information is given to you, you know it's a weak acid or weak base right away. What is that?
pH.
Is it pH? Anyone?
What about the Ka or Kb value,
Okay.
maybe?
So if a Ka or a Kb value is given, you can be 100% sure that it is a weak acid or a weak base. Okay? Why? Because if you have a strong acid or a strong base, it doesn't have any Ka or Kb. Okay? So, what do you have? If you have a weak acid or a weak base, you have a Ka, because Ka has something to do with the dissociation of acid or dissociation of base. And usually Kb value are small value. And the way you interpret them, the higher the Ka, the stronger is the weak acid. The lower the Ka, the weaker is the weak acid. So even though you still have a weak acid, you can still compare the strength. You can still compare which one will dissociate more with one another. Okay, so let's try to have a review on this concept. So how are we going to answer this question? What is the pH and maybe pOH of a 1.5 times 10 to the 3 negative 3 HCl solution? So maybe here it's quite easy. You have an HCl, it will dissociate to give you H plus and Cl minus. So if you have 1.5 times 10 to the negative 3, it will give you 1.5 times 10 to the negative 3, because this is a strong acid. And all you need to do is just use this. pH is equals to negative log of H plus. And if you're going to substitute it, so you have here 1.5 times 10 to the negative 3. So this will give you what? If you have your calculator. So you will get here around 2.82, right? So if you remember the significant figures for this, so you have your 1, 2. So whatever the number that you're given here, you're going to put it as the number after the decimal point. Okay? Now, if that is the pH, what will be the pOH? So pOH is just equals to what?
14 minus pH.
14 minus the pH. So this will give you around 11.18. Okay? So everyone still knows this concept. How about this? Combining what we have learned from last week. Calculate the pH of a 0.1 molar HBr using activity coefficient. Okay? So what would be the ionic strength here? Anyone? What's the ionic strength here?
We got to use that table, don't we?
Yep. But what's the value that we're going to use to compare or to get the activity coefficient? So as you could see here, you have a 0.1 molar. So if you're going to get the concentration to get the activity coefficient, you're going to use the one that is 0.1. Okay. And the activity coefficients that you're going to have there will be around 0.83. So that's the one that you get from the table using the ionic strength of 0.1. Now, how are we going to put the pH here now? If you recall, this is last week's lecture.
It's going to be negative log.
So we have negative log.
Right. In parentheses, the molarity, which is 0.1 because it's a strong acid.
So, negative log H plus times
the activity coefficient.
The activity coefficient. So if you're going to do it this, we have this one, okay? And then we multiply it with 0.83. And what do you get?
Do we multiply the log product by the coefficient?
You have to multiply first the 0.1, get the negative log, 0.1.
Okay. Okay, so I got 0.83.
Trying to see 0.1 times 0.83 log. So have to check the thing. I think you have to do this first and then get the log.
Yeah, I think so too. That makes more sense. It gives a different number.
Okay, because you will get the right answer should be 1.08. So just check it just to be sure. Because if you're going to get the negative log first, that will give you 1. So times 0.83, that will give you what? 0.83. But you have to multiply 0.1 times 0.83% and get the log. Is that clear? Now, how about this? So what is the pH about 1.0 times 10 to the negative 8 molar NaOH? So what's the problem that we have with this thing? You cannot say it is 6. Okay? Because if it's 6, you have here what? A strong base. And you say if it's 6, that is what? Acidic. The answer there should be still basic with a pH that is higher than 7. Why? Because you have there a strong base. So what we have here is some sort of a problem wherein NaOH is not the only source of your hydroxide. Okay? So this is a case wherein you are in the intermediate concentration. So what do you need to remember if you have a situation like this? Because you cannot have a 1 times 10 to the negative 8 with acidic pH. Okay? So the thing that you need to remember is there are 2 reactions that are important in this system. And what are these 2 reactions? These 2. Okay? So your hydroxide is not only coming from sodium hydroxide. there's also a hydroxide coming from water. So in case like this, you're going to use the systematic treatment of equilibrium. If you're going to recall what we have discussed last week. Okay? So what do you need to remember when you have this systematic treatment? So you have to write all pertinent equilibrium reactions. Okay? So we could say the main reaction that we have here is not the NaOH, but this one. Right? Although we could put the NaOH there, but as you could see, it's not even a system at equilibrium because it is a strong acid, so it will going to be like this. So what's the next thing that we're going to do? Okay, we write the charge balance. We're going to write the mass balance. So we're going to predict. So we're going to predict what will be the main product. Okay, so how are we going to set up this CBE and MBE? Anyone? How do we write CBE? And then how do we write MBE? CBE, you have what? You have H plus, and what's the other positive charge? Anyone?
Sodium.
Okay.
Na
You
plus.
have Na plus, and the only negative charge is your hydroxide. Okay. In your mass balance, what is the one that is given? The NaOH concentration. So you can put there Na plus is equals to 0.1. Or no, not 0.1. 1.0 times 10 to the negative 8 molar. Analyze. Because the next thing that you're going to do is we're going to set up the equation. So, what can we say about here? So how many equations do we have here now? We have this. We have this one. We have this one. And we have this. So how do we set the equilibrium constant expression here? Anyone? In this reaction here, which one do you know? The equilibrium sting. Between the two. Can we say KW? KW is equals to what?
1.0 times 10 to the negative 14.
No, I mean before we put the number. KW is equals to the product of the concentration of H plus and OH minus. Right? And this is equals to 1.0 times 10 to the negative 14. So we already set up the pertinent equations that we have here. Or another thing that we can do is instead of putting the NaOH, because we said, where's the water that we have there? So we can put the water on that one. And what is usually given here? NaOH plus water. Or we could just say the OH minus plus water. Is it Ka or Kb? What's the K that we have there?
Kp.
Usually we have there the Kb. Okay, so you have, if you're going to look at it, the Na plus times the OH minus over the NaOH, or maybe we can ignore that thing, but we're going to look at here. So what are we going to do here now? What's the assumption that we can have here? Can we make an assumption here between the H plus and the OH? Which one will be greater? Are they equal? Is the amount of the H plus and the hydroxide in the system the same? Yes or no? Anyone?
No, it should be basic, right?
Okay, so the answer there is no. Now the question is why?
We added more hydroxide anions from the sodium hydroxide.
Okay, you have more hydroxide because there's another source of hydroxide. Water is the source of the H plus and hydroxide. But in addition to water, you also have sodium hydroxide. So you can have that assumption that hydroxide is greater than H plus. Okay. So with that assumption, what are we going to do? How are we going to represent the hydroxide and the H plus? So remember, usually we set it as like this. Kw is equals to what? X times X equals to 1.0 times 10 to the negative 14. Now, how are we going to represent this one? Are we going to represent this as X times X? So what happened here? One is still an X, but the other one will be X plus what? Anyone? So question with this setup. Because what will happen, this will become X squared, okay, plus 1.0 times 10 to the negative 8x minus 1.0 times 10 to the negative 14 equals to 0. Okay? So the question now is, what is the x that I'm solving for? X is equals to what here? Anyone? What is the x that I'm solving for? Your x is equals your H plus. Because I set up the other one as x plus 1.0 times 10 to the negative 8, and that is your OH minus. So what you're going to do, okay, using the, what do you call this? Quadratic formula? You should be able to get what is x. and the X value that you have there, that is equals to H plus. And once you have that, you'll be able to get around this value, 9.5 times 10 to the negative 8 molar, giving you a pH that is equals to 7.02. Okay? Anyone? Question? So I will do it again. In a step-by-step manner. Okay. So if we're going to look at the thing, so we're going to write all the pertinent equations. So what's the equation that we have? So we have the KOA, the NaOH. So this is aqueous producing Na plus and OH minus. So both of them are aqueous. And then you have the water, which dissociate to give you H plus and OH minus. So here we could say we can have one equation and three unknowns. Okay, so what else is going to provide here? Kw is equals to H plus times OH minus. So we have K plus, H plus, and OH minus. And then we need two more equations that we have here, so we can have the CBE. So the CBE, if you're going to look at this, this is just K plus H plus equals to OH minus. And then we have the MBE, and this is just not K plus, Na plus, okay? So you have here Na plus is just equals to 1.0 times 10 to the negative 8 molar. And then we can solve starting with the CBE. So if we have a CBE, how are we going to do it? Let's say we have it H plus equals to OH minus K plus. Does this equation make sense? Where did I get this? I just rearranged that thing. Okay. Now, what did I do here? So maybe I can replace this with this equation. H plus equals to Kw over H plus minus, I always use the K plus because that's the one that I used previous semester. Okay, so where did I get the Kw over H plus? Anyone?
You rearrange the Kw is equal to H plus OH minus.
This one. Because I want to express the OH minus in terms of H plus. Okay? And then maybe what I do, by putting or removing the H plus here, what did I do? I multiply both sides by H plus. And what happened? This cancel out that one. So I have here an H plus squared KW, okay, minus Na plus times H plus. Does this make sense? So what I did, I substitute for the OH minus, and then I multiply by H plus both sides, and now I rearrange them. Okay, so I multiply it, so I got this one. And what I'm going to do is I'm going to rearrange them. Okay, where I have an H plus squared plus Na plus times H plus minus KW. So this is just the same as the one that we did earlier. So what did I do now? I just replace this with X. And then I know this one based on this MBE, 1.0 times 10 to the negative 8. Okay. And then X. And then minus, I replace KW with the value that we have. So I just calculate for the X, which is my H plus. So I just did the problem once again, just for the sake that you know how to get problems like this. Okay? So when do you use this type of calculation? So when the concentration is near 10 to the negative 7 molar, we use the systematic treatment of equilibrium to calculate the pH. And at still lower concentration, the pH is 7.0, set by the autoprotolysis of the solvent. So you do it, okay, when you are at least in this range of concentration. Now let's go with the weak acid and weak base. So again, this is just a Gen Chem 2. So for the reaction, HA dissociating to H plus and A minus, we set up and solve the equation. So usually we have it set up like this. But right now, we can set it like this one. X squared, because you know the X here, and then you have here F minus X. So F minus X is just whatever the initial concentration minus the X that you came from here. And you get the Ka. So again, I told you this is not new to you. Okay, the new one to you here is maybe this one. The use of F. F is the initial concentration that is given. So let's try to solve this one. Find the pH of 0.05 molar trimethyl ammonium chloride given the pKa of 9.799. So how are we going to set this up?
First, I think the first step is setting up the Equilibria equations.
Okay, so you set the equilibrium here. So this is what? A base, trimethyl ammonium. So if you're going to look at ammonia, all you need to do is replace it with CH3. Okay, and you have here an Na plus because the other one is a chloride. So when you dissociate this, this will give you this dissociation. And if you're going to look at this, you have what? At the end, this will be your F minus X, and this will be your X. If you recall the ice, right? So this is already the equilibrium. In the ice, if we're going to do it, or if you're my student, I call it the rise. Okay, so you have here an F, nothing, nothing, and then the changes that you have here an minus X, and then you have here a plus X, a plus X. So you end up with this. So this is still a Gen Chem one. And then you're going to put here. So what do you have here? This is still a Ka. Okay, because you have here an acid. So if you have that, Ka is equals to H plus and the NCH3 there over the NCH3 H, or X squared over F minus X equals to, how are we going to get 9.79 converted to its Ka?
So we can substitute F. We can substitute F for the initial concentration, right?
Yep.
Or
so this is equals to 10 to the negative 9.799. And then I can replace this now with 0.05. So what is the X that I have here? So you cannot make an assumption now that this is very small compared to that one. In your Gen Chem, you can make that assumption that the X value is so small that 0.5 minus X is still 0.5. But here, as much as possible, you cannot do that. So you have to do a quadratic formula in solving this equation, in solving for X. Okay? So I leave this up to you how you're going to get the X there using the quadratic formula. But the X value that you will get there would be around 2.8 times 10 to the negative 5. And if you're going to get the pH of that, no, not 5, 6. And if you're going to get the pH of that, that would be equals to what? Anyone?
.55.
Okay, so you have there 5.55. So I leave up to you from here how you're going to get the X. You can arrange them in the form like this. And then use the quadratic formula. And I think you can make the assumption here. Why? Because the value of your X is really small. But that's not always the rule at this level. I don't know if you know what I'm talking about, wherein the 0.05 that you have just equals to 0.05 that we do during the Gen Chem. Okay. So it just happened here that in this example, the X value that you have there is really small compared to the initial concentration. So if we're going to look at here, we can also get the so-called fraction of dissociation. So the reaction that we have, a certain fraction of the initial concentration of the weak acid exists as a conjugate base. So this is known as the fraction of dissociation. And if we're going to get what it is, it's just this one, X over F. Okay? So this is in terms of conjugate base. So if you're going to look at the conjugate base, so you have this conjugate base over conjugate base times the initial concentration, or the concentration of the acids at equilibrium, not the initial concentration. So if you have it here, what will happen? This will just be cancel out. So you have X over F. So if you're asked what is the fraction of dissociation for this concentration, so you will have what? 2.8 times 10 to the negative 6 over 0.050. And that would be equals to what?
5.6 times 10 to the negative 5.
So we have here 2.8 exponent negative 6 divided by 0.05. I got 5.6 times 10 to the negative 5. Anyone got other answer? Yeah, that's the solution to that. So we could say here 5.6 times 10 to the negative 5. So this is what? 1, 2, 3, 4, 5. That's the fraction that dissociate. Analyze. To those, what's so quiet there? Now, what does this tell us? So if we're going to look at the amount of weak acid that exists in the conjugate base form, it depends on the pH of the solution. Okay, so if we're going to look at the Ka expression, this is what we have. Now, from this, we can derive the relationship between the concentration of the H plus and the dissociation fraction, or fraction of dissociation that we have here. So we start with the Ka and the definition of the alpha value. So if we rearrange this thing, so this is just putting this here, you end up with this, right? So in the alpha definition that we have the conjugate base over the concentration of your reactant plus the conjugate base. So what are we going to do with this one? We can simplify this by dividing all of them by A minus. That's why you have here a 1 and a 1. Because you divide this by A minus here, you divide this by A minus here. But when you do that, you also divide this by A minus. That's why you end up with that one. And what do? You have an A minus over HA here, so that is equivalent to that one. We substitute this with this, you end up with this one. So HA over A minus, so that will be H plus over KA. So once we have this, okay, so we have this equation, and what do? We're going to replace it with the given value that we have there. And from this, we can get, okay, what's the pH if we put the fraction that dissociate. So here, what does it says? In order for the alpha value to be 0.5 or higher, the hydrogen concentration or the hydronium ion concentration must be no higher than 1.59 times 10 to the negative 10. So I think that's the one that is new to you. So this is just knowing what would be the ion concentration if we want to know the fraction, or if the fraction of dissociation is given. Okay? Now, how about weak base? So what we have so far is weak acid. So what we do now is weak base. So again, this is your Gen Chem 2. So instead of a Ka, when you see a hydroxide, that means it's a Kb. So if you have this dissociation, so you have a base reacting with water, you produce an H plus with the base and an hydroxide. And if you're going to look at the Kb, this is how you put them. But just like the Ka, we're going to put the concentration of your given species as F minus X, which is the initial concentration minus the amount that dissociate. And you can calculate also Kb, if you recall, before, by dividing Kw with Ka. I don't know if you still remember that. Okay, but I have a sample here on how you're going to calculate the pH of a weak base. So we have an example of a weak acid here. We also have a weak base. So if you're going to write the formula for this, or the equation, you have NH3 reacting with water, giving you what? Anyone?
NH4 plus hydroxide.
OH minus. If you're going to look at the ice, so this is what? 0.1. You don't have anything here. And then this is minus X. Okay. And this is plus X, plus X. So you end up with 0.1 minus X, and you have X and X. So this is your F minus X. And if you're going to look at the Kb, so you have your X times X over F minus X. So that's X squared over 0.1 minus X, and this is equals to 10 raised to 9.245. Oh, wait, because this is what?
That's for the pKa, not for.
That is your Ka.
Yeah, exactly.
So to determine Kb, so you can put here 1 times 10 to the negative 14 divided by 10 raised to the 9.245. So you have to be careful on the given value. Okay? So once you get that, you're going to solve for X. And your X rare is equals to the concentration of your hydroxide. So what is Kb?
I got 1.76 times 10 to the negative 5.
Okay? So what's the X that you get there? Anyone, what's the X? So this is the value that I get for the X. So once I have the X here, I can get the POH. Now you might ask why POH? Because the X value that I have there is for a hydroxide, not a hydronium ion. So getting the X there, negative log 1.32 exponent negative 3. That is going to be around 2.88, which I'm going to subtract with 14. So the pH that I have here is 11.12. Analyze. Ask if you have question. Question. Question? So we go now to another topic that was discussed already in Gen Chem 2. We're going to go on these so-called buffers. So buffers is a mixture of weak acid and its conjugate base, or we could say a weak base and its conjugate acid. Now the source of that conjugate base or conjugate acid is usually salt. Okay, so what does buffer do? They resist changes in pH, because what will happen is its component will react with the added acid or added base. So for the dissociation of the weak acid, HA producing H plus and A minus, okay, we can determine the pH using the Henderson-Hazelback equation. So maybe this is not the first time you heard this equation. So Henderson-Hazelback equation. So this is equals to pH equals to pKa plus log of A minus over HA. Okay, so this equation is not new to you. You encountered this in your Gen Chem 2, and you will encounter this again when you go to your Biochem, the Henderson-Hazelback equation. So this is one of the useful equation that you should know. Okay, so if you're going to look at here, pKa, that is usually the negative log of Ka. So this is unique to weak acid. So every weak acid has their own Ka value. Okay, and the concentration of HA and A minus are essentially unchanged from those used to prepare the solution. So let's try to solve some buffer problems. Okay, so the buffer problems that we have here is a little bit deeper or more challenging compared to what we have discussed in Gen Chem 2. So for instance, this one, sodium hypochlorite, the active ingredient of almost all bleaches, was dissolved in a solution buffered to a pH equals to 6.2. So find the ratio of the hypochlorite over hypochlorous acid in this solution, given the Ka of the hypochlorous acid as 3.0 times 10 to the negative 8. So how are we going to solve this problem? What's the approach that we have here?
We should write down that equation, the Hasselbalch equation first. Just write. Yeah, we should just write it down to work
So
with
if
that.
we're going to look at this, we could say maybe get the pKa. So get the negative log of 3.0 times 10 to the negative 8. So I'm going to call one by one. Okay, so that Brian is not the only one answering. Lawrence, what's the number that we get from this? So you have to be wake up. Maybe that will be the quiz for today.
7.5.
Okay. 7.5, another number after 5. Because
2.
you need two significant figures.
7.52.
2.
Yes.
I'm just going to let go of the ambulance here. Okay, so now we have the 7.52. How are we going to set them up in the Henderson-Hazelback equation? We have the pH, We have the pKa. So how are we going to set it up? Angel.
Sorry, I was writing down. Can you repeat what you said?
So how are we going to set up the value in the Henderson-Hazelback equation? So this is the Henderson-Hazelback equation. So we have this. We have this. So how are we going to set it up now?
So it'd be 6.2 equals 7.52,
Okay.
and then plus log, and then the concentrations.
Which we don't know.
Right.
Okay. So this is how we have it right now. I'm just trying to, because of the, I hate my writing font. So this is now its form. Okay. So what do you think the next step? So who I'm going to call? John.
You can subtract 7.52 from 6.2, and then you can just solve for the ratio.
Okay. So how will I'm going to set this up? Maybe this going there? Like
Yeah.
this? So I end up with a log here. So how will I remove the log? So I think I'm going to get what? This is a negative here, 6.20. Okay. So I will have a negative here. So the question now is, how am I going to simplify this expression? Who's the next one? I'm going to have a roll call to everyone. Kyle. So everyone will be awake.
When you raise both sides to the power of 10,
Okay. So if I do this to this one, this will be cancel out. And what do I get? 10 raised to 1.32. What's the value that I get, Kyle?
0.048.
Okay, thank you. So what does this 0.08 means? Soyon, what does this 0.08 mean? So once you have this number, what does this means now? How are you going to interpret this? Soyon, are you there? Oh, your mic doesn't work. So type it. What does this interpretation means? What does this number means? How am I going to say this? What does this mean? Sam, are you there?
Yeah, I'm here.
Yeah. So what does this mean? How are we going to interpret this thing?
Um,
So what do you think the value of your HOCl here? If you're going to move it like that.
it's the ratio. It's like the total ratio.
Yeah, so what, because this one would pertain to OCl minus. So what do you think the HOCl value here?
I'm not sure.
You're not sure? Bailey?
I'm not sure either.
Brian? Go back to Brian.
I I don't know honestly. Yeah, I'm sorry.
Is it
That's
one?
one. What does the 0.048 mean? So for every one of HOCl, that means there's a corresponding 0.048 of OCl minus, right? Because 0.048 divided by 1 is 0.048. Does that make sense? Everyone?
Yeah.
Yes.
Okay. Because the one that you have here, find the ratio of your conjugate base over the acid. So since it's given there as 0.048 as calculated by Kyle, so that means for every one of HOCl, the corresponding conjugate acid is 0.048. Okay? And this is set up by the pH that we set. Okay? So what else do we need to know? The conjugate base of a weak acid is a weak base. And the weaker the acid, the stronger the base. However, if one member of the conjugate pair is weak, so it is conjugate. And you always have the relationship between the Ka and the Kb from this. Okay? So we all know Kw is equals to Ka times Kb. So if you're going to get Ka, I think there's something wrong with this formula here. So if you want to get the Ka, so that is just Kw over Kb. Oops, what's that? Raining? Okay. And when a strong acid or base is added to weak base or acid, they react nearly completely. So whenever you have a strong acid or strong base, there's a reaction to completion. Unlike weak acid or weak base, there's always an equilibrium. So let's look at another base or buffer problem. And I'm going to call you again. Okay? Just to make sure you understand. So here, if we add 12 ml of 1 molar HCl to a solution containing 12.43 grams of tris with formula mass of 121 1.135 and 4.67 grams of tris hydrochloride with formula mass of 157.596 in 1 liter, what will be the new pH? So maybe the first thing that we're going to do is we find first the initial pH of your buffer before adding the 12 ml. Okay, so the thing that we're going to have here, so this is what? A tris and a tris hydrochloride. So how are we going to get this thing? So everyone is in 1 liter. So Tris would be 12.43 grams over 121.135 grams per mole. And then all of them in 1 liter. So that means the concentration is molarity. And then the other one, 4.67 grams over 157.596 grams per mole over 1 liter. So who will I call that I have not called yet? So everybody, calculate the Tris, and Jennifer, calculate the Tris HCl concentration. And then we go back again with the calling. So this is our quiz for today. But I don't have quiz for you today. So I'll just roll call you. So you're forced to be awake. So anytime the two of you are ready, you can say it over the mic or put it in the chat.
For the cheese, I got 0.1026.
0.0.
0.1026.
0.1026. And Jen typed there 0.0296. Hanbo, how do we set them up?
I don't know.
What is missing? There's still missing information here.
PK.
What do you think is the one missing? If I set it up like this.
Yeah, like PKs, and I think we're missing the PK.
So what is missing? What information that you need here that is not given?
PKs, no, we know the concentration already.
Yep, but there are some things that you still don't know. You're looking for the pH.
Yeah.
So what else is the one that is not given, that should be given? So we have this. That's
Yeah,
the one that we have there.
PK.
So we don't have the pKa. Okay. So the pKa should be given to you here. So I'll just put it here as 0.8.072. Now, Daria. Okay. How do we assign the numbers that Jen and Avery calculated here?
So like 0.1 is on the top and 0.03 is on the bottom.
So it's like this?
Yeah.
So what we're doing here, we're just calculating first the buffer pH, not the main problem yet. Okay? Because you have to do it that way. So once you have this one, you can now calculate the pH. So what's the initial pH of the buffer? Anyone? Because you need to do the calculation here. Someone answered. So 8.612. Okay. Very good. So that is your initial buffer pH. So what we're going to do now, I just have to discard this thing. so that I can clean it up. Okay, and then I'll share it again. So what we're going to do now is we're going to solve the problem now that we have the initial value that we have there. So how are we going to solve this one? So we can set it up. Okay, so we have there the buffer plus H plus. Okay, so remember, if I add an H plus, which do you think will react? Is it this tris or the tris hydrochloride? Which do you think will react?
Just tris.
Hmm?
Tris.
The tris. Okay, and when they react, they're going to produce the tris hydrochloride. Now remember, they're already in 1 liter. So whatever the molarity numbers that they have, that's just moles over liter. So we said B earlier is 0.0 or 0.1026, and this one is 0.0296 moles. So this is the initial one. So we're now solving for the main problem. So how many moles of H plus do you have? Anyone? How will I get the number of moles of my H plus?
Use the molarity of HCl multiplied by the volume in liter.
Okay, the same thing that you do in your laboratory. So 1 molar times 12 divided by 1,000. So I have here 0.012. So everybody knows where I got that? So what will happen? So what are the changes that will happen here? You're going to use up all of this. So that means you're going to subtract it with this, right? How about here? What happened here in BH plus? So if you use this up, this will be the amount that will be formed. Make sense? So in the end, the final that you have there, you subtract this one, so you have what? 0.1026 minus 0.012906. And this one is 0. And this one is 0.0296 plus 0.120. So I have 0.1496. Oh, wait, I think I messed up. 0.0296 plus 0.012 there. 0.0416. Analyze. Does the value make sense? Because the next thing that I'm going to do, I'll go back to the Henderson-Hazelback equation that we have. So I said here 8.072, so plus log. So this is now what? 0.906, and this is 0.0416. So what will be the new pH value? Anyone?
8.41.
What? 8.41.
41.
Now, what do you think will be the pH if it's not buffered? Anyone who wants to answer that question? If there is no buffer, what do you think the pH will be? Anyone wants to answer that question? What do you think the pH will be? Anyone? The pH would be 0 because it will be made up of what? The 1 molar HCl. Okay? Or since it's going to be diluted in 1 liter, so if it's just HCl, it's just going to be 0 because negative log of 1 is 0. But if you're going to add 12 ml to 1 liter, so the pH should be around what? Anyone? What do you think is the pH? So you're going to get what? The negative log of this number here. And that would be equals to what?
0.92.
Okay. So you have a pH equals to 1.92. So see the difference if the system or the solution is buffered compared to the one that is not buffered. Okay. And what do you think is the buffer system that we have in our body? Anyone? Before we solve this last, oh no, not the last, the second to the last problem that we have here. What do you think is the buffer system in our body? Anyone? What keeps our pH equals to 7.2 to 7.4, even if we have too much to eat?
Isn't it don't our kidneys maintain our pH
Yeah,
balance?
but what's the buffer system that we have there?
Is it carbonate ions?
Nope. Okay. I think biology will help you to answer that question. So what do you think is the buffer system? So maybe this will be asked in your exam in the Blackboard thing. Okay. So before we answer that, let's try to solve this problem. I think I have mistakes here. Discard. That should be NaOH. So how many ml of 0.5 molar NaOH should be added to 10 gram tris hydrochloride to give a pH of 7.60 in a final volume of 1.20? So here, this is a preparation of a buffer wherein you use right away the hydroxide. And if we're going to write them in terms of the equations that we have, so you have there the hydrochloride reacting with the hydroxide to give you the tris and water. Okay? So the question that's being asked here now is how many ml of 0.5 molar of NaOH should be added to 10 grams of the tris buffer? So you should have the formula mass of the tris HCl here, which is equals to 157.956 or 596. So this is from the previous problem still, just like a continuation on that one. So what we need to do here is we need to get the initial moles of each of the buffer system. Okay, but unfortunately, you don't know how much is the hydroxide. But you should know this one. How many moles is that? So this will be what? 10 grams divided by 157.596.
0.063
0.0634
634 35 if you
or
round
maybe
it.
35
Yeah, if you round it, yeah.
if you round it up. Okay. Now in the final, what will happen? You don't know the x, so that will be minus x. For the b, that will be plus x. So this is forming a buffer using a tris hydrochloride with the hydroxide. So what the hydroxide do is you're forced to form the tris. So this will become minus x, right? So this will be out. So in the final here, you have 0.0635 minus x, and this is x. So that's the thing that we're going to use in your Henderson-Hazelback equation. So Henderson-Hazelback, you have pH equals to pKa plus log of B over BH plus. So what's the pH?
7.6.
Okay, so you have 7.60. And pKa, the one that we used previous problem, the same setup or the same buffer system. So we have here now this thing, log of x over 0.0635 minus x. So analyze. Because if you have this in your take-home exam, you might be worried at the instance, oh, how do we set it up? Okay. So the next thing that we're going to do, 7.60 minus 8.702, right? And on the other side, this one. And maybe I can just make a shortcut here. So what's the 10 to the negative number that you get from here? What do you get? 7.60 minus
1.102.
8.702.
1.102.
1.102. And if you get the 10 to the negative 10.102, that will give you what?
0.
0.8.
Yeah.
0.08?
08.
Is it 0.8?
Yes, 0.079, but if you round it, 0.08.
I'm just trying to double check my value here. $7.60 minus 8 point. Oh no, this is the mistake that I have. That's why. My fault, 8.072. Okay, something is odd. 7.60 minus 8.072. I just want to double check. Oh, we don't have the previous problem now because I erased. So what do I have now? This is not 1.102 now. This is what? Since I changed the value here.
Negative 0.472.
7.60 minus 8.072. So that's negative 4.72. Which is 10 will give me 337.
Yep.
So what will be the x if I'm going to rearrange this one? What's the x value that I will going to get? Because I can rearrange it like this is 0.0214 minus 0.337x, right? If I'm going to cross multiply it with that number, so I have x minus 1 minus 0.337. So I have here a 0.663x equals to 214, which I divide with 0.663. What's the x that I got? Anyone?
Zero point zero three 2 3
0.337 times 0.0635, 0.0214. So 1 minus 0.337663. You get this? No. 32 only.
Yes,
0.0323.
Yeah. Yep.
that's
So what does it tell us? So it tells us that's the x value that we have. So it tells us that you have 0.0323 moles. So what you're going to do now is determine the ml of 0.5 molar. Because that's the concentration of your sodium hydroxide. that you used to add with things. So how are we going to do that? Are we going to divide or multiply with 0.5? Does this make sense?
Yeah, because we set the 0.032 equal to 0.5 over x, and then you just rearranged it.
You cancel the moles and you have the 1/1 per liter. So
Yeah.
this will give you around this value. So what does it mean? You're going to get 64.6 ml, add it with 10 grams of Tris buffer, and then dilute it to 250 ml. Okay?
What does the X equal to? Isn't it the concentration of tris hydrochloride?
Yeah, but that is also the concentration of your NaOH. Not the concentration, the moles. That's the amount of your hydroxides that react with your BH plus, and that's the amount of B that was produced.
Right. Because their molar ratio is 1:1, so that's why they're having the same moles, right?
Yeah.
Okay. Right, you use the moles divided by molarity, it gets the volume that you need to. All right.
Okay? So this one, I'm going to leave to you. Maybe that will be the assignment that I'm going to give to you. Okay. So that is the chapter that we have here. Oh, by the way, before we finish the chapter, okay, more about the buffer. So this is in the concept question. So the pH of the buffer is nearly independent of dilution, but the buffer capacity increases as the concentration of the buffer increases. So what does it mean? Whatever the concentration of your buffer system, it will give you to that pKa value, or whatever is the pH of that pKa value. However, the strength or the capacity of the buffer, okay, depends on the concentration. What does it mean? The higher the concentration of your buffer system, the more it can resist drastic pH changes. Okay? Because there is what we call a limit to the buffer. As you're going to look at our calculation, once the amount of the acids or the bases is higher than the buffer system, it can drastically change the pH. Okay? So the way that it looks here must have more moles of buffer present than there are moles of acids that could be introduced in the solution. So once the moles of the acids or the moles of the base, remember in the calculations that we have here, okay, there's a time that the number of moles of this is much higher than the one that you have here. And when that happens, okay, the buffer will not do its job because it's already overrun. Its capacity is already overrun. Okay, so if you're going to look at the maximum buffer capacity, usually it's pKa plus or minus 1. So you can only use buffer based on its buffering capacity. So at every pH, there's usually an associated buffer that you can use. If it's pH 4, you use the citrate buffer or the acetate buffer. If it's pH 7, you can use the phosphate buffer, which is the buffer system in our body. Okay? Phosphate buffer, that's the buffer system. And then I asked you about biology, because in the biology you have learned about ATP, ADP. And the P there represents phosphate. Okay? And if you have a pH 10, I think the buffer that you use there is the carbonate bicarbonate buffer. So if you're going to choose a buffer system, you choose a weak acid or conjugate base system with a pKa plus or minus of the desired pH, and you look at the component, the exponent in the Ka value. It should be close to the pH that is desired. Okay? So if you are asked here what weak acid would be appropriate for making a pH equals to 10, okay? So what you're going to do is you're going to look at the appendix, and the one that is closest to this one is this buffer system, because its Ka is 5.7 times 10 to the negative 10. Okay? So that's the first chapter that we have for today. But we have the other one, and the exam that we're going to have what in 2 weeks, as you agree last time, will end in this chapter. The next chapter is the polyprotic, but the coverage of the exam is monoprotic. Okay, so we're going to take a 5-minute break, and then we're going to resume with the polyprotic acid. Which is this one. So this is just a continuation of what we have discussed. There's just some addition, but the concept is still the same. Okay? So let's have a 5-minute break. Okay, so let's assume so polyprotic acid. So how is this different from the monoprotic acid? Anyone?
They have multiple protons to donate.
Okay. So polyprotic acid, they have multiple protons to donate. Monoprotic is exclusively what? One hydrogen, involving only one hydrogen. Polyprotic, it can be diprotic, it can be triprotic. Okay. So the difference of this one is this is what? More than one. More than one proton. So if we're going to look at this diprotic and acids and bases, okay, so we have here polyprotic acids and bases are those that can donate or accept more than one proton. If it's two, we can call them diprotic acids. If it's three, okay, we can call them triprotic acid. But the one that we want to look at today, aside from the known diprotic like sulfuric acid, oxalic acids, and known triprotic acid like phosphoric acid, the one that we want to do is the type of polyaprotic acid that deals with the so-called amino acids. Okay, so if we're going to look at these amino acids, usually they are neutrally charged acids. So there are at least 20 amino acids, of which 10 of them are essential. So when you say essential, they should be provided to us, or the body cannot synthesize these essential amino acids. So if we're going to look at the amino acids, okay, you can have a charge on this one. It's like the alanine for itself, there's an H2A plus. Okay, so that's the type of polyprotic acids that we're going to focus on today. And then we have the diprotic acid like sulfuric, oxalic, and then carbonic acid. And then we have the triprotic acids, which is your phosphoric acid. So if we're going to look at the amino acids, they are the building blocks of what? Building blocks of what is amino acid? Anyone?
Proteins.
Biomolecule.
Proteins.
Okay. So that's the building blocks of your proteins. And if you're going to look at the amino acids, they have this carboxylic acid group, which is acidic because of the word acid there, and the basic amino group. And in addition to these two groups that they have this substituent known as the R. And the fourth one that we have is just a hydrogen. Okay, so the carboxyl group is a stronger acid than the ammonium group, so the non-ionized form rearranges spontaneously to have this so-called sweeter ion, which contain both the positive and the negative sites. So if you're going to look at the amino acids, this is how it looks like. So this is the carboxyl group, and this is the amine group. The one that differentiated the amino acid is the R group. Okay? So I will not ask you to memorize because we're doing open notes for the exam. So if we're going to look at the groups that we have here, the ammonium group, it has a pKa around 9.5. And the carboxyl group, it has a pKa around 2.5. And these are the acid dissociation constants of your amino acids. So that means if you have a polyprotic acid, you also have more than one pKa. And the pKa that they have here, one is the carboxylic group, and the second pKa has something to do with the ammonium group. So in most of them, there are always two pKas. If ever there's a third one, that third one came from the R, containing either an acidic group or an amine group. So you seldom see amino acids having more than 2 pKa. If ever there's a third pKa, that third pKa came from the R group, the substituent group. So having known this one, okay, if we're going to look at the amino acids, so we could say this is how their form looks like. So this is the acidic amino acids, and this is the basic amino acid form. But in the neutral form, this is what they have. So try to look what happened here. As the pH increases, you lose H. Now, does that make sense? At higher pH, you don't have H. Does that make sense? At higher pH, they are deprotonated. Okay? So remember, H has something to do with what? Being acidic. So at lower pH, you see here, you have the two hydrogen. Now, after it passed through the first pKa, one of the hydrogen was removed. And the one that is removed is from the carboxyl group. So what happened? You have a negative sign and a positive sign within the amino acids. That's how we end up with this so-called sweeter ion concept. Okay? And then if you're going to keep making it basic, you're going to lose the amine acid or the amine proton. And what you have here now is a negative sign. So if you're going to look at this positive, 0, negative charge. Okay, and this is true for the other diprotic acid and bases. Okay, so if we're going to look at the reaction that is happening here, so remember the ampiprotic that you learned from your Gen Chem, wherein acid, ampiprotic substance or substance that can act as acid or a base, depending on what's the other chemical that is being react to them. So that is what ampiprotic acid, ampiprotic means, or amphoteric, I think is the other term that you use for any substance that can act as an acid or a base. Now, let's go to leucine. So leucine is one of these amino acid. Okay, so if you're going to look at the leucine, following the system that we have here, so the one that is only different here is the R. Okay, so if you have a leucine, the order would be equals to CH2, CH, CH2, CH2. That's the R component of your leucine. Now, if we're going to look at the Ka value of that leucine, the first Ka value is 4.7 times 10 to the negative 3. The second Ka is 1.8 times 10 to the negative 10. So at the protonated leucine, that's H2L plus. It reacts with water, you lose one of the hydrogen, so you form HL and hydronium ion. Now, continuously, you react that HL with water, and you form hydronium ion and the L minus. So the sweeter ionic form of your leucine would just be in the form of the HL. So what are we going to do with this thing? Okay. So what we're going to do is we're going to calculate the pH of the following 0.05 molar aqueous solution. The protonated leucine, the sweeter ionic leucine, okay? Now, sodium leucinate is the what we call negative charge of leucine, and just the leucine. But what we're going to do now is we're going to put it as H2L plus, HL, and L minus. So this is your H2L plus, this is your L minus, and this is your HL. And you're given here the pKa. So I think it's already there. So the way that we're going to do is we estimate the answer and then we calculate it. So we're going to need the pKa value. What does the pKa represent? Anyone? Before we calculate them. What does the pKa represent? Anybody? At pKa, what does it mean? Or let's say at pH 2.328, what does it mean? And at pH 9.744, what does this mean? Anyone? So at pKa 1, it means that there's the same concentration of H2L plus with HL. And at pKa 2, there's the same concentration of HL with L minus. Right? Remember, Henderson, Hazelback, you have it like this. When does this value equals to 0? Anyone?
When the ratio is 1.
When the ratio is 1. Or when A minus and H minus are the same. So that's what the pKa interpretation is. Okay? So the question that being asked now is, at what pH can we find this different form of leucine at 0.05 molar, given the pKa? Okay? So we have this diprotic thing. Okay? We can also get the Kb1 and the Kb2. Remember, we have a conjugate acid-base pair here. So how do we get the Kb1? It's just Kw divided by Ka2. And we get the Kb2, okay, by just dividing Kw with Ka1. Okay? So, how are we going to do the thing? So we could use the systematic treatment of equilibrium, which is an equation that we have what we called discussed last week and some of them today. But instead of doing that, we can make a simplification. Okay, so instead of using this, H plus equals to Ka1 times Ka2 times the initial concentration plus Ka1 times Kw over Ka1 plus the initial concentration, we can just get it like this. Okay. What does this value answer? Which part of this that equation give us an answer? Anyone?
Is that an answer for 3 for Lucian?
Okay. So this one answers the question Lucin solution. So if we're going to do the systematic thing, just for the sake of you seeing it, okay? So we just replace the value that we have there, the Ka1, Ka2, which is just the value that is related to this. I think it's given here at the beginning. That one, 4.7 and 1.80. And then the given concentration plus 4.7 times 1 times 10. That's a Kw times, if I'm not mistaken, okay, that's Ka1. Just to give you an idea where they get this. And this is Ka1. So the value that you get for that is this one. But if you're going to do, okay, pH is just 1/2 of the sum of pKa1 and pKa2. It's almost close to it. Okay. Now the question now, okay, we solved this one. How do we solve the first two? So the way that we're going to solve the first two is, the first one, just like any monoprotic acid. Okay. The second one has something to do with hydrolysis. So if we're going to do this thing, where's that Ka1? So we have that. So 4.7 times 10 to the negative 3 equals to, what do we have? X squared and then F minus X, right? So you have here 4.7 times 10 to the negative 3 X squared. So what is the concentration that we have? 0.05. That's the setup. And all we need to do is find X. And X is what? Your H plus. So what is X from the setup that we have there? Oh, excuse me. So you need to use the quadratic equation. So X is equals to giving me a pH equals to what? Anyone?
1.88.
Okay, 1.88. So we can put this now as 1.88. The other is 6.04. So the next thing that we're going to do, sodium leucinate. Where's the space? I need some space to answer it. Okay, so maybe I use this one. Sodium leucinate. So I can go with this value because the one that I'm calculating is L minus. And if I follow this one, so I have what? KB equals to HL times hydroxide over L minus, right? Which just be X over, or X squared over F minus X equals to 5.5 times 10 to the negative 5. And then you calculate for X. And your X there is what? Your hydroxide concentration. What's the X? So what's the X that you get there? Anyone? If you use the quadratic equation, the X here would be around 1.64 times 10 to the negative 3. And that is your hydroxide. So what would be the pH corresponds to that value? So what's the pH? You get 11.21.
Yes.
So I get the POH first, and then from that, I get the pH.
How
So-
did you get the POH again? I'm getting something different. I don't know where I'm messing up.
The POH is just the negative log of 1.64 times 10 to the negative 3. And then I subtract that with 14, so I get the pH. So you get the POH first. And then you subtract 14 minus the POH to give you the pH. Okay?
Okay, I got it.
So the way that you're going to do this thing, if you're calculating, if you're asked to calculate the pH of a different form of acids and base, diprotic acids and base. So if it's in the acidic form, you calculate this as a monoprotic acid. It is in the basic form. I don't think base hydrolysis is the thing there. You could just calculate it as a base. If it's the intermediate form, so you just get the average of the 2 pKa. So for instance, if you're asked to do this thing, the same thing as what we did, okay? So they just misaligned. They should be like that. And given this value, this is the answer that you have, but I want you to work on it. Because one item in the third exam is a question like this one. Okay? So the easiest one that you get there is the 6.11 because it's just the average of these two. But the other one, you just use them like a weak acid calculation, and this one just like a weak base calculation. And you might be asked here to describe how would you calculate the pH of the following aqueous solution. So sodium monohydrogen phosphate. So what does this mean? What's the charge?
1 minus.
Okay. So you may ask, how are you going to calculate this one? So maybe you start it from here. Or maybe it can be like this. Sodium dihydrogen phosphate. So how are you going to calculate this one? So this is what? The second thing. So this is the second calculation. So you might be given here what? 3 pKa? So it's between the first and the second Ka value. Glycine hydrochloride, so it is just like a monoprotic acid. So you just have a glycine here and an H+. So when dissociate in water, it will give you glycine and H+. So this is just a monoprotic acid calculation, and the same thing with this one. But this one, trisodium citrate. So what does this mean? So you act this as a monoprotic base. And the potassium hydrogen phthalate. And again, this is also a monoprotic acid. So whatever the concentration, you just do the thing that Ka is equals to x squared minus over F minus x. If it's a base like this one, so you have Kb equals to x squared F minus x. If this is this one, so it's just the average of the pKa that you have, where you can find those species. Okay, so if you're asked to describe, so we could say this is what? Amphiprotic, Ka1, Ka1, and then Ka2. I think this is not the Ka1. I think this is also an amphiprotic thing. Right? So you have to look at the Ka1 and Ka2. So that's how we're going to solve them. Now, can we do a buffer from this polyprotic acid? The answer is yes. Okay. And it's a little bit tedious because you're going to have what? 2 Henderson-Hazelback equation. So if we know H2A and HA minus, then we can use the pKa1. If we know HA minus and A2 minus, then we can use the pKa2, like this one. So it's just tedious, but you can do that. Okay? Just following this Henderson-Hazelback equation. So for instance, if we have a problem like this, find the pH of the solution prepared by dissolving 1 gram of potassium hydrogen phthalate and 1.2 gram disodium phthalate in 50 ml. How are we going to solve this problem? This is a diprotic system. So if I have a Henderson Hazelback here, all you need to do is determine, am I going to use the pKa1 or am I going to use the pKa2? So you look at the materials. So you have where? Potassium hydrogen phthalate. And then the other one is disodium phthalate. So KHP will dissociate to give you K plus and HP, right? Now HP will dissociate to give you H plus and P2 minus. So what are we going to use it? What pKa are we going to use it? pKa1 or pKa2? Anyone? Because what if I gave you here Ka1, Ka2, and the corresponding mass of these two? So let's say I have this. So this is the one that I'm asking you the question. And I'm just going to put the numbers that we have here. So you have what? 1.20 grams divided by 210, 0.94 grams per mole. And this one is 1.0 grams divided by 204.221 grams per mole. So the question now is, which one we are going to use? I'll make a roll call. Or you can, what we call, put your answer in the chat. Ka1 or Ka2? Because that's the setup already. But the question now here is, which pKa will I use? Is it pKa1 or pKa2? And that's the system that we have. So I want you to input your thing. Is it the second or the first pKa?
Second.
Okay. How about the others?
Are we all wrong?
No, nah, I'm just smiling. So remember, the system that you have there would have what? An HP minus coming from KHP and a P2 minus coming from Na2P. So you're going to use the second one. Because in the exam, I can give you Ka1 and Ka2. And if you didn't understand the question, you're going to answer it using what? Ka1 or Ka2. But the right one would be pKa2. And if I'm going to give you the value is around 5.408. And just I want to work out. I think it's 5.47, the answer that you get for the pH. So this is the pKa2. We can also do it like this one. This is what? A triprotic system. So the leucine that we have, okay, we have only what? A diprotic system. So what's the difference of diprotic with triprotic? You have an additional H plus. Now the question that you should ask yourself here now, how are you going to solve a triprotic system? Okay, because what you have here now, you have three forms. 1, 2, 3, 4. So at least for the first one, this is what? This is a monoprotic acid. So whatever is the Ka equals to x squared over 1 over F minus x. So you get the x there, you get the H plus, you get the given pH. Now, how about the others? How are we going to solve the other things that we have here? For this histidine thing. So what's the next thing that we can solve here? The last one? Right? The last one would act as what? The histidine plus. You treat it as Kb. So we could say this is Ka1 and this is Kb1. So whatever the X that you get, that is equals to your hydroxide. Now how about the H2H plus and the HHS? How are we going to treat it? This should be a negative, not that's a mistake there. How are we going to solve this one? Anyone? What have you learned if it's an intermediate of a polyprotic acid? The diprotic acid that we have. How did we get the pH of the intermediate form? Although we have a systematic treatment, but we didn't really do it. What we did is we just show you the what? 1/2 of pKa plus pKa. The same thing with this. So for H2S plus, it's 1/2 of pKa1 and pKa2. And for HHI, it's 1/2 of pKa2 and pKa3. That's the answer that you need to do. Okay, so when it's an intermediate, all you need to do is look at the average of the pKa that is involved on that thing. Because what does it tells us? If we're going to look at this in terms of composition. So you have here H3H2 plus, H2 histidine plus, H histidine, and then the histidine minus. So what is in between them? Ka1, Ka2, Ka3. Okay. So as I've told you, Ka1, you have the same concentration of this and this one. Ka2, the same concentration of this and this one. Ka3, the same concentration of this and this one. So if you're looking for the pH for this one, it's the average of Ka1 and Ka2. For the pH of histidine, okay, that is just in between Ka2 and Ka3. So when you are in the Ka1, that's the half point between the species in between them. If you are in Ka2, that's the half point between this and this one. And if you are in Ka3, that's the half point between this and this one. So if the pH is higher than pKa3, so the main composition of that is histidine minus. If the pH is less than pKa1, then most of them are this form. Okay? Because the next thing that we're going to do is you should be able to determine what is the principal species in a given solution. So what does this mean? What is the form, okay, of the given diprotic acids and bases that exist in a given pH? And the only information that you have is the Ka value. So for instance here, what is the principal form of benzoic acid which has a pKa of 4.20 at pH 8? So what does it mean? Benzoic acid, you only have two forms. It can be HA or A minus. Now, the pKa that you have there is 4.20. So what does it mean? At 4.20, you have equal amount of your HA and A minus. Now you are asked at pH 8, which is the one that is present at greater form, or what is the principal species. So since there are only two species that you have there, and the one where they're 50-50 or the same is 4.20, so at pH 8, you can say that the A minus is the principal species. So this is how you interpret them. The pKa, that's the pH where there's the same concentration of the two forms. Higher than that, the other one is dominating. Lower than that, the other one is also dominating. Okay? So for instance here, alanine. What is the principal form of alanine at pH 8? What is your answer? So if you're going to map them, so you have 2.34. So that's the pH where you have equal amount of HA and H2A. At 9.87, that's the equal amount of HA and A minus. So if you have pH8, if you map them, predominantly they are, or they exist as an HA. So that's the principal form of alanine, pH8. So if we have the triprotic system here, this is how it looks like. So the more acidic form and the more basic form. So I'm trying to see if there's, okay, I'm going to ask the question now. So ammonia. At pH 7. What is the principal species? Given pKa equals to 9.24. So what's the system that you have? Anyone? NH4 plus NH3. And the pKa is 9.24. So what is the principal species given pKa equals to 9.24? You can answer in the chat, but please don't follow the first one who will answer it there. And everyone will just follow the thing. How about the others? Okay, so as you could see here, at pH 9.24, they have the same amount. Now, since 7 is less than 9.24, so that means NH4 plus is much higher than NH3. So that's the predominant or principal species. That's what it means. Okay? So these are the questions that you have in the blackboard. Now, the question now is, can we determine the fraction that we have? Because what we have right now is just qualitative question. What is the predominant or what is the principal species given the pH and provided the pKa? So what if you're asked, what fraction do you have there? Can we do that? So for instance, the question that we have earlier, benzoic acid at pH 8. Okay, we can derive the equation to give us the fraction of each species of an acid or a base. So remember the one that we have earlier? The alpha of the acid or the alpha of the conjugate base. So all we need to do is just what? The HA over the initial equation. Or if we're going to break them down, this is just the acidic form plus the acidic form plus the Ka. Now, if it's in terms of conjugate base, this is just the Ka over the sum of the H plus and the Ka. So if we're going to apply this to the questions that we have earlier about benzoic acids, all we need to do is we put them the value that we have. So we said at pH 8, okay, it exists as a benzoate. So we're going to use now the formula that you have here. So Ka over H plus Ka. So you have there 10 to the negative 4.20 over 10 to the negative 8.0 plus 10 to the negative 4.20. And you have here almost 99%. Now let's do it with the ammonia that we have, the questions that we have here. So 7.07 and pKa of 9.24. What fraction of ammonia do you have, or what fraction of the ammonium ion exists at 7.7? So which one are we going to use? I think we're going to use this one, right? So you have the 10 to 7.07 divided by 10 raised to 0.07 plus 10 raised to 0.9.24. Oh, I hate it. Whew. I don't know why the writing for doing this. So what do you get?
Zero 0.993.
So what does it mean? At pH 7.7, almost 99% of the ammonia form is in the ammonium form, or of the ammonia is in ammonium form. And if we're going to look at the plot or the graph to it, it's like this one. So that's how you have if it's a monoprotic acid. So if it is a diprotic system, this is how you're going to do it. You have this, okay? Remember the ax squared plus bx plus c. So it's the same thing. You just replacing, if it's H2A, that's the one here. If it's HA minus, that's the one that's in the second one. And if it's C, that's the one in the third one. And if you're going to look at the plot of this one, this is how it looks like. And there is a method that they use because of these properties of amino acid. Okay, they call it the isoelectro. They take advantage of this isoelectric and isoionic pH. Okay, so what they look at this isoelectric and isoionic pH, the way that they look at it is take advantage of the pKa of a given amino acids. And once they have that thing, they be able to separate the amino acid that is present in the solution. So for instance, for the alanine cation, so this is the pKa. For the alanine anion, this is the pKa2. So what does this mean? So this is where these two concentrations are the same, or these two forms are in the same concentration. And this one, these two forms are in the same concentration. So what they do when they're talking about isoionic point, okay, so this is the pH obtained when pure neutral polyprotic HA is dissolved in water. And the only ions that you have there, H2A plus, A minus, H plus, and the hydroxide. So if it's in the alanine, okay, most alanine is in the form of HA, and the concentrations of H2A minus and H2A plus and A minus are not equal to each other. So if you're going to look at the neutral alanine dissolved in water, the pH should be somewhere pH 2.234 and 9.87. And that is the so-called isoionic pH. So it's just equals to your pH equals to pKa1 and pKa2. Okay. Isoelectric point, on the other hand, that's the pH at which the average charge of the polyprotic acid is 0. So most of the molecules are in the uncharged form HA. And the concentration of H2A plus and A minus are equal to each other. So they have this isoelectric focusing as a method that they use to separate this material that they have. So isoionic point, the difference between the two, that's the pH when pure neutral polyprotic acid, okay, or the sweeter ion is dissolved in water. Isoelectric, that's the pH at which the average charge of the polyprotic acid is 0. So if you have pure sample of neutral alanine and you dissolve it in water, the A minus would be slightly larger than the H2A plus. And by adding a small amount of the acid, some of this A minus would be converted to H2A plus until the concentrations are equal. Okay, so the isoelectric focusing, that's the one that they use for separation of proteins from one another. So this is the chapter 9. And I don't know, do you want this to be included in the exam? And then we focus on titration for the third exam and electrochemistry. What do you think? What do you think?
I think it makes sense to put the
because what happened is you're going to study again for the third exam something about acids and base, because the next chapter that we have is all about titration. Although there's still an acid-base titration there, but it's not the same as this one. But since we finished already and you have 2 weeks to prepare, so maybe we can include this one in your second exam. So you just focus on titration for the third exam, titration and electrochemistry.
Okay.
Okay. Because I may give you a buffer system that is monoprotic, and then in the third exam, I'm also going to give you a buffer system that is diprotic or triprotic. So at least if you just put together that thing, so everything will be what? From chapter 5 to chapter 9. And we will have a review next week, just in case. We go over the quizzes and the assignment that we have, just to prepare you. because next week is just an introduction of titration. And then after that, we have the exam. So we might not going to meet in 2 weeks because you're taking the exam. And then after that, we have the acid-base titration. And then after that, we have the electrochemistry. So titration is a lot, to tell you frankly. This is a lot, but titration is also a lot. Okay. So this is how we end this chapter. So there's 2 who are absent. So those who are here, you get something in the quiz. I don't have a quiz today, but those who I asked, I called, and those who answered the thing, that will be your grade. And then I'm going to have 2 assignments, 1 for each chapter. Okay? So I'll try to post it by tonight. So question. I have not what we call added yet the thing, and I think it's working on my part because at least I don't know who's the good one and I don't know the not so good one. At least for me. There's no quiz today because the one is already graded. I called all of you, so that's the quiz that you have. You end up with 100. So it works for me by not knowing the mean of the exam. But I think no one didn't, fail the exam from what I know. Because if I see some that's really not what we call did well, I will know them. So the score is between the 2, right? You have the Blackboard score and the take-home score. So when you add them together, that's it. Because if I'm not mistaken, it's 70 plus 30 to give you 100. Okay. So as of now, no one is failing the course. But that doesn't mean you have to be lax, because the difficult exam is the second exam. But that was during the time when they don't do it take home. So I expect a much better result with what we call a take home exam. Okay. So question? If none, then I'll see some of you on Wednesday. Okay. No, I have not looked at the score yet. Okay. I'm worried about it once I look at them. Okay. So if none, see you next week.
Thank you.
For others on Wednesday. Just wait, Lawrence. Okay.